Okay, welcome everybody. Today we're going to be going over the first set of analysis that we're going to be doing for the Ragnarok TCA. Today we're going to be covering Ansys thermal analysis and then some Ansys structural analysis. We'll be going through the entire pipeline, including where we're getting our sizing data from. That will be RPA, to kind of a quick rundown of the CAD model, and then we're going to be importing that into Ansys and running said simulations there. First, I want to go over some of the specifications for this current version of the engine. So we're using a chamber pressure of 500 psi, an oxidized fuel ratio of 2.2. We're using obviously liquid oxygen and liquid jet A. Here's the nozzle conditions, so contraction area ratio of 8, which is fairly high because we need to be able to fit our entire engine in specific length for the print bed. Nozzle exit conditions are 1 atmosphere, and our ambient conditions are 1 atmosphere. The thrust chamber is sized for 2,000 pounds of thrust and has a characteristic length of 1.2. Okay, so here's our thermal analysis settings. So we are going to apply chamber cooling. We are using both regenerative and film cooling. We are going to use the combined convective heat transfer model. The regenerative cooling has been made by RPA. Here are the settings there. Basically, we're flowing all the fuel through the regen channels. And then the film cooling is using 10% of the relative chamber mass flow rate. So once we have all these settings in, we can go up here and we can run the analysis. Here we will output a bunch of information regarding the combustion characteristics, the performance of the engine, and then here is the thrust chamber size, and here's the thermal analysis. These are the two slides that we really care about the most. From the thrust chamber sizing slide, we can take these variables and we can directly put them into the parametrized Ragnarok TCA CAD. So for example, DC, which is the diameter of the chamber, comes straight from RPA, and you can go through each of these numbers. They are in order, and you can just straight import them into Onshape. And this is what that chamber looks like, if it will load. Actually looks like. So we have our regen channels, our holes for connecting to the injector. We have our fuel annulus at the front and a port for our fuel to flow into. If we do a cutaway of this, we can see kind of what the inside looks like, although that's not the best cutaway. Let me get a better one. And there we go. If we do a cutaway of this, we can see kind of what the regen channels look like going up through the TCA. This is made up of a number of splines. And then for the purpose of simulating this in Ansys, we actually don't need to simulate the entire 360-degree radial revolution of the TCA. So instead, we're just going to take a roughly 40-degree section to reduce the amount of time that it takes to do and run simulations. So if you want to just simulate just a section of the TCA, you can come down to revolution, and you can just reassign this to 40 degrees, press enter, and then when we go over to the thrust chamber and we let it load for a little bit, we can see now we have just a 40-degree section of the thrust chamber. So yeah, and so this will be a lot easier to mesh and a lot easier to run, given how intensive some of these simulations can be with Ansys. This is the same model that we would use for the coming thermal, structural, and CFD analysis. So yeah, once you have that model, you can come over here and you can press export. Okay, so now we can open up Workbench. Make sure that if you're not on Tamu Wi-Fi that you are using VPN. Okay, the first thing that you're going to do when you get into Ansys Workbench is we're going to come over to Steady State Thermal Analysis, and we're either going to double click or we're going to drag that up and create a standalone system. Next, we're going to go into Geometry. We're going to double click on Geometry. And we double click on Geometry, we'll see that Ansys Discovery will start, which is where we will import our model into. Okay, once you get into Ansys Discovery, you're going to come up to the File menu in the top left-hand corner, and then you're going to click Insert Geometry. We can then go find the geometry file that we just made, and we're going to import that. Once we import that, there's one important thing to take note of here, and that is where the global coordinate system is. So here the global coordinate system is placed right at the bottom of the TCA, which is actually fine for us. And pay attention to the fact that the Y direction is pointing out of the TCA. That's going to come in handy later when we start creating loads onto this TCA. Once you have the model imported into Ansys Discovery, we can go back to Workbench and we can click on the Model tab. So once we're in Ansys Mechanical, you can see that our geometry is automatically imported from Ansys Discovery. And now we're going to generally start at the top of these tabs and move our way down. So we'll start at geometry. Down here, the only thing that we care about here is the material assignment. So we can go to structural steel and we can change this to something more fitting. In the future, if we use a material like GR-COP42, we will have to add our own custom material to Ansys. But for the purposes of this simulation, we're just going to use copper C18200. And then we can see that that has now changed. Under materials, we can see that it was added. So when creating a new coordinate system, right click, click insert, click on coordinate system. And then down here, we're going to create a Cartesian coordinate system. We're going to define the geometry that the Cartesian coordinate system is based on as being the top flange of the TCA. And then we can see that Y points down, but we start at 0 at the top of the TCA. Okay, so after we've defined our coordinate system, we're then going to define our mesh. So first we're going to insert, we're going to go down to method. This is going to be the automatic method. So after we go here, we're going to go to geometry. We're going to make sure that we're selecting bodies, and then we're going to click on our body. We're going to click apply. Next, we're going to go to sizing. We're going to insert a sizing method. We're going to go over here, and we're also going to select our body again. We're going to define the element size as 1 millimeter or 0.001 millimeters. And then after that, we're going to go up to mesh, and we're going to click generate mesh. This process probably will take a couple minutes to fully mesh. Okay, so that took a couple minutes, and now that it is done, we can see that we have quite a fine mesh here. We're going to make sure, importantly, that the regen channels are reasonably meshed. So you can see that the mesh is struggling with the channels, or the fillets, on the edges of the channels. This is okay for this first pass analysis, but later when we do CFD, we will need a much finer mesh, and that will contribute to much higher computational times. But for this is actually fine for our Ansys structural and thermal analysis. So now that we've done our mesh, we can come over to steady state thermal and we can start importing our thermal loads. So if you go to the DCR to Ansys thermal analysis loads, we can see that we have a convection load around the fuel annulus, which is the ring up here. That's going to have a film coefficient of 8,000 and a temperature of 300 Kelvin, which is the inlet temperature of our fuel. The regen channels are also going to have a film coefficient of 8,000, and their temperature we are going to get from the coolant temperature in RPA. The external surfaces are going to have a film coefficient of 30 and a temperature of 300 K due to natural convection from the environment. And then the internal heat flux loads, we'll have two of these. There will be one on the fuel annulus, and then there will be one on the inside of the chamber. We will get the total heat flux from RPA, and we will import it into Ansys and use that for our heat flux loads here. Okay, so how do we actually get this data from RPA into Ansys? Let's start there. So the first thing I want you guys to do is I want you guys to go and open up a new Google Sheet file and just leave it blank for now. And then we're going to go back into RPA. So we're going to go to thermal analysis, and then we're going to select and copy all of this data. To do that, right-click any cell and then click Copy All. Once you've done that, you can come over here and you can paste all of the data. Boom, we got it all right there. A couple things to note. The location here starts from the injector side and moves out towards the nozzle side. So in this case, we can use that coordinate system that we made to make our lives a little bit easier here. There's a couple values that we care about. We care about total heat flux. Total heat flux is what we would use inside of the chamber. And then we also care about TC, which is the temperature of our coolant. Notice that total heat flux is not in the correct units, so we will have to change that. And we will need to make this so that we can easily import it into Ansys with correct units. So go over to here and we'll do total heat flux. And this is where we will convert from kilowatts to watts. So total heat flux right here, we're going to multiply this by 1,000. And then we will autofill. Perfect. So now we have our total heat flux in watts per meter squared, which is the same units that we're using in Ansys. So we do also need to convert the location into meters instead of millimeters. So we can insert a column to the right. And then we can select location meters. And then we can take our value over here and divide by 1,000. And then autofill. We can go back into Ansys and we can insert a heat flux load. We can select the interior surfaces of the chamber. So go up to select face and then click Control and individually select all of our chamber faces. Then go over to geometry and click apply. Under magnitude of heat flux, we're going to come over here and we're going to select tabular. The independent variable of which will be the y direction. And instead of using the coordinate system based at the bottom of the chamber, we can change the coordinate system to the one that we created that starts at the top of the chamber to follow the RPA notation. Perfect. So now we have our location in meters. We have our heat flux in watts per meter squared, and we have our coolant temperature in Kelvin. So to add the heat flux load, we're going to select all of the location in meters, and then we will also select all of the total heat flux. Once you have both of those selected, you can just press Control Copy, and then you can go over to Ansys Mechanical. You can go to the tabular data section over here, and you can just press Control V. Boom. So now we have just imported the heat flux loads from RPA straight into Ansys. We can see exactly what it looks like on the outside of the chamber, and we can see what the cross-sectional heat flux loads look like. Okay, so that is the first heat flux load from the inside of the chamber. The second one is on the fuel annulus. So you can see that the combustion chamber ends here on this circular fuel annulus section. So we expect to see a fairly significant amount of heat flux on this section to about the endpoint here. And so in order to simulate that, we're going to take the lowest heat flux that we see over here, and we're going to apply it going down the other way. First, we're going to go look at the maximum heat flux at the end of our chamber, which is roughly 1.8 million watts per meter squared. So we're going to use that as a starting point, and we're going to basically go make a distributed heat flux to 0 at the end of the fuel annulus. So we can go to Insert, we can go to Heat Flux. We can select our geometry, being the end of the annulus. The problem with applying this heat flux load to the annulus is that the annulus geometry wraps around the entire thing. In reality, we would really only see heat flux load to about the midpoint. This can be revised with future revisions of the parametric TCA, and hopefully we'll do that in the future, but I have not done it yet. So for now, we will just apply a simple distributed load here. So we can go down to magnitude, we can click tabular, and independent variable, we can click the y direction. So now our coordinate system starts right at the bottom here. And this ends about 7 or so millimeters after the end of the thrust chamber. So we can go down here, go 0.007, and then we can select a heat flux at the midpoint of 1.8 E6. And then at the end we can select, let's pick a reasonable number around 100,000, 1E5. And then anything above 0, we want to essentially have no heat flux. So we're going to go negative 0.0001, and we're going to put a heat flux there of 0. Actually, we could put, we'll click 0. So this is kind of what that looks like. It's a little bit uneven, obviously, because we get heat flux on the other side. In fact, this 7 may need to be a little bit larger. It may need to be closer to 10. Yeah, so that looks a little bit better. This is not the best approximation, but in the future, we can hopefully make this better and not have this crazy heat flux over here. But for now, this will do. So the next thing that we're going to do is apply a convection load on the outside of the TCA, and to do that, we're going to go to Insert, we're going to go to Convection, and then we're going to select the external parts of the TCA. And we will include the fuel annulus for this actually too. We're going to click Apply, and then we're going to set a film coefficient of 30 and an ambient temperature of 22, which is fine. So the next load that we're going to add is the convection cooling load from the regen channels. To do this, we're going to go up to our steady-state thermal analysis. We're going to go to Insert, Insert Convection, and then we're going to select all of our regen channels. Remember to press Control so that you can select multiple geometries. And you can also click Control to move around by using your middle mouse scroll wheel. And then we can come down here and we can select the inside of the fuel annulus. And then we can go over to Apply. To film coefficient, we're going to set this at 8,000. Notice that the ambient temperature is 22 degrees Celsius. We will need to change this so that it is tabular. So go to ambient temperature, click tabular data, and then go down here and click edit data for ambient temperature. Select the independent variable as y, and then select the global coordinate system as the coordinate system that we made earlier. So now we can go back to our spreadsheet. So we see that TC, or the temperature of our coolant, is in Kelvin. We need to convert that to Celsius by subtracting 273. So we can do that. We can say TC in Celsius. And then minus 273.15. Okay, so after we have our coolant temperature in Celsius, we're going to come over to location. We're going to select our location in meters, and then we're going to press Control, and we're going to select our temperature. And we're going to click Control Copy. We can come over to Ansys Mechanical, go to the first cell here, and do Control Paste. So now we have our temperature varying with location. If we come up to Home and we select Section Plane, we can actually cut this down the middle and see what it looks like. There we go. So now we can see how the coolant temperature changes with time. In reality, the film coefficient will also change with time, and you can actually vary that also by going to the tabular section. The problem is the film coefficient is determined through CFD throughout the channels, and we in this analysis will not be finding the film coefficient. That will be later when we do conjugate heat transfer analysis with Ansys Fluent. So be aware that the current limitations of this analysis is basically that This analysis favors larger region channels because there's more area. In reality, the film coefficient is a function of the velocity of the fluid through our channels, and so the larger we would make our channels, the smaller our film coefficient would be. So be aware that this analysis is not necessarily perfectly indicative of what you would actually see, and that you do need CFD analysis through the region channels to find your film coefficient. But we will be doing that in a later analysis. This is mainly just to teach the basics of thermal and structural analysis. Okay, so now that we have our data for film coefficient and our temperature through our region channels, we can go to solution, we can go to insert, and we can add temperature. If you want to edit the section planes, you can come down to the section plane tab and select or deselect and draw new section planes. Okay, so now that this is all ready to go, we're going to right click here and press solve. Okay, so the analysis is pretty much done and we are writing our results file. The thermal steady state analysis really shouldn't take more than 10 or 15 minutes to run. Depending on your computer, it could be significantly faster. Okay, so now we can see what the temperature of our TCA actually is. So here it's kind of hard to see because of the mesh. So we can come up here, we can click results. We can go to edges and we can click let's go show undeformed model. And then let's click contours and let's go smooth contours. And then now we actually get to see what it actually looks like. So we can see obviously the highest temperature is at the throat, and generally we decrease throughout. So if we want to cut this inside and take a look, we can go to the section plane, and then let's make a cut right at the throat. Now we can see how the region channels, which look a little bit funky here, are dissipating the heat away from the inside of the chamber to the coolant. And then through this cross section, we can also see how after the region channels, generally speaking, the temperature is much, much cooler. Okay, so now that we've done our thermal analysis, we want to move on to our structural analysis. So we can go up to analysis, we can click static structural, and that will add a whole new analysis down here. And if you go back to your project, you can see that we have imported the engineering data, the geometry, and the model from our steady state thermal analysis. And now we can do static structural analysis on top of this. We can also import the actual results from this thermal case study into the static structural analysis. So the first load that we're going to import or insert will be our pressure load from the inside of our thrust chamber. So the first thing that we're going to do is we're going to go here and we're going to select the entire inside of our thrust chamber. Let's get rid of our section plane. We're going to click apply on geometry, and then we're going to create a distributed pressure here. The pressure up to the throat will be 500 psi, and then we're going to linearly ramp that down to 20 psi at the end of the throat. The exit pressure is calculated to be 14.7 psi, but in order to be a little bit conservative, we're going to make that 20 psi at the end. So the first value that we want to find is we want to find where the throat is. So we already selected the magnitude of our pressure is going to be tabular. The independent variable is going to be y. The global coordinate system is going to be the coordinate system we created, where the y0 is at the top of the flange. And then we can go into RPA or our parametrized CAD model, and we can find where LC is. So LC will tell us the distance from the back of the chamber to the throat. We can see here that that value is 180, let's call it 187 millimeters. So we can go over here and we can type in, we can convert that to meters, so 0.47. And then from 0, we can set the pressure to 500 psi, 500 here. And then we need to know what the end of the TCA is too. So the end of the TCA is LE plus LC. So LE is 129 millimeters. So 129 plus 187 is 316 millimeters roughly. So 0.31, let's call it 315. And then we're going to make that 20. So perfect. Now we have our pressure load distributed from the end of the chamber all the way down. We can say it looks about right too. This might be a little bit off, but this is probably about where we want it. The next load that we're going to add is the pressure load inside of the regen channels. So for the purpose of this analysis, we're going to assume that there's roughly a 50 psi drop through the regen channel. So the first thing we're going to do, we're going to go insert, we're going to go pressure, we're going to select all the regen channels, and we're going to select the inside of the fuel annulus. We're going to click apply. Under magnitude, we're going to go to tabular. Under independent variable, we're going to go to Y, and we're going to select the previous coordinate system. Okay, so we know that the bottom of our vehicle, so we know that the bottom of our TCA is 0.315 meters, and we're going to set the pressure to the inlet pressure of the fuel, which is 650 psi. And I just realized that the pressure here are in pascals. What you can do if the pressure is in pascals but you want psi is we can go over here. We can select psi. We can go import our loads in psi, which will be 500, 520. And then we can go and change back to our metric units and they'll convert. So we're going to do the same thing for the other one because I forgot about the units. So this is supposed to be 600 psi at the top and 650 psi in the annulus. And now we can convert that to metric, and that will convert it over to pascals for us, so that we don't have to worry about that. And we can see that the highest pressure is in the fuel annulus and the lowest pressure is at the top of the regen channels, and it all looks pretty good. Okay, so next we want to add our fixed support. Our fixed support is going to be to the top of the injector. We can insert a fixed support, then select the top face where the injector would interface and click apply. So because we are simulating this system as just a 40-degree section of the TCA, we need to add frictionless support loads to the outsides, or to the cross sections. We can then click apply, and this will allow the TCA to expand in the radial direction, but won't allow it to come detached from the wall, which is a reasonable boundary condition if you cut the TCA out. Okay, so now that we have all of our loads added, we can go and we can add things that we're looking for. So we care about total deformation, we care about strain, we'll do equivalent bond misses, and we'll do plastic. Equivalent plastic. So equivalent plastic will show us our plastic strain, which is nice to have. We'll go under stress, we'll do equivalent bond misses, and then we'll go and we'll do vector principle and we'll do error. This first analysis, we're not going to include our thermal loads, but if we wanted to do that, we would go import load, import steady state thermal. We will do that in a second though, but for now, I just want to show you the structural loads real quick. We can then go and we can either go on the static structural tab, or we can go down to the solution tab, right click and press solve. This one will take quite a while to solve, so just be prepared for that. If you want to monitor the progress of your solution, you can go down to Solution Information. Under Solution Output, you can select Force Convergence, and this will tell you whether or not your simulation is converging. And you'll see that here in a second when the data points populate. Okay, so now we can see our force criterion graph and our force convergence graph. Anytime the force convergence point is lower or smaller than the force criterion, a substep will converge, and this means that our entire simulation is converging. And so you can see that under time here, our time step has also gone up, and once our time reaches 1, the simulation will be complete. Okay, so it looks like the simulation has fully converged, and we are currently evaluating our results. So this is what our force convergence graph looks like. You can see every single iteration we had converged by quite a large margin, so that is all good news. And in a second here, we can look at our results. Obviously note that these results do not include thermal stress, which is a fairly significant stress here, but this is still very, very useful for determining how the various stresses in our system contribute to the overall stress. So you can see that this is a little bit larger deformation than we would actually see. These results are scaled roughly 100 times the normal deformation. So if we want to see the true deformation scale, we can come up here and select true scale. Obviously, this is not nearly as bad. We're basically seeing 0.17 millimeters of deformation, which is pretty insignificant, all things considered. It's a little bit odd that we see it much higher right here. Here we can see our elastic strain. You can actually see the individual regen channels and how they affect the overall structural integrity. Equivalent plastic strain. So this is a great indicator of if your system is plastically deforming anywhere. See here it is not. Here is equivalent stress. We can turn this into PSI by coming down to the units here and changing it to this bottom one. So we can see that we pretty much stay under 10 KSI, which is actually good. Generally speaking, we want to stay under 10 KSI without thermal loads. That's actually a really, really good place to be. And then if we want to add probes and actually see what results are in certain areas, we can come over here to the probe. We can also remove the maximum and minimum sections. And we can actually see where stresses are at various locations here and analyze them. So you see we do see some stress concentrations over here, which probably aren't indicative of actual real stresses. We can come down to section planes and see what the inside of the regen channels look like. And we can see that this is actually pretty reasonable. There's definitely some room for improvement probably in this fillet, and we can see that most of the hoop stress is still being taken by this outside portion, which is good. And the regen channels, you can see the difference in stress between the regen channels and the spot where it's just solid is a couple hundred PSI throughout. See, it's more stress in some areas than others, depending on the regen channels. If you want to come down here and delete the probes, you can just come down, shift select all of them, and then delete them all.